questions, and feel free to interrupt me, and I will do my best to explain. So my talk is regarding about the cross-layer optimization for AI with an algorithm and hardware co-design. In fact, the co-design concept has been popped out even since I was a PhD student many years ago. At the time, I have been working on circuit and architecture co-design. And right now, with our technology development, I feel like the stack and the layers and within the stack kind of grows. So first of all, I'd like to give a very brief introduction on the AI systems and its relationships to the device and circuits and the architecture. So this is a very conceptual call. One of the reasons I start with the device and array is I have been working on processing in memory designs. So with especially what we call emerging memory 20 years ago, like with all these new materials and device and innovations, we try to leverage those devices and to build up the arrays and for information processing. And of course, combining array and controllers, and we build processing engines. And then integrating memory with the processing engines, and we build up the processing cores. Of course, the current computing systems consist of the many cores. Well, through this thread, the capacity of information processing grows fast. But as you can see, when we really handle from device and to the entire systems, the order of the number of transistors or devices and could be like billions or tens of the billions right now. And that's the power of the hardware systems and for tremendous AI applications. The figure on the right-hand side actually was a little bit out of date, but the concept here is still remain valid. What we find is when we're talking about the hardware designs, the efficiency and the flexibility is always a trade-off. For example, the hardware platforms used for AI applications have been advanced significantly fast in the recent years. But simply we can catalog and still in traditional ways, right? The most powerful are GPUs. GPUs are extremely fast, but we all know they have a very high power consumptions. And most of the times when we use GPUs to train the AI applications or DNN models. Well, FPGA have been used like at the cloud or the edge a lot in recent years. The advantage of FPGA is it can provide massive parallel processing. Power consumption is much lower compared to the GPUs. And of course, it can be reconfigured for the dedicated applications. So generally speaking, some people likely to use it for perception applications and like processing the DNN models, while using FPGA for trainings is still kind of a hot topic. And of course, an ASIC can always be taken as the most efficient designs. I think if you already have a dedicated design model and the data sets, of course, an ASIC is the most efficient ways. However, the development of dedicating ASIC designs takes a longer time, and therefore it's not so kind of adaptive to the fast evolving AI region right now. My research actually has been focused on the novel architectures and also emerging devices. So I've been working on processing in memories and particularly focused on RAM, resistive memory, and magnetic memory before. Well, so back to today. today's talk, in fact, I like to emphasize the importance of co-design between the algorithm and hardware level. And I will give a few examples and the examples across in a few disciplines. I will start with how to craft efficient AI algorithms, and then goes to the co-explorations in between the soft and hard side. At the end, I also like to give a few examples, like applying AI on real-world applications, and they are very beneficial. Well, first of all, start with the compression techniques. And this is how I start with the AI and hardware co-designs. In fact, it's been a few years, and back to 2015, our group has been collaborate with the Intel group. Even at the time, people realized that the DNN models has a high redundancy in trying to compress the model. So particularly at machine learning communities and who work on software side without much knowledge about the hardware, they propose a lot of the compression and pruning technologies. The interesting part when we work with industry is when we applying this and compress the model on hardware and execute it, test its runtime, what we find is, and its runtime to speed up, is not tremendously increases. In fact, in a lot of cases, the real runtime is longer than what we got than before the compression. Well, the figure actually, the purple curve show the sparsity rate, so the higher the better. So you can say for many layers, and we can remove 90% plus parameters. But in fact, it doesn't lead to the speed up. So at the time, we're trying to figure out what was the problem, and essentially, it's because algorithm only, the sparsification technology, didn't consider the hardware overhead. So on the right-hand side, basically shows the convolutional layer matrices, and based on the convolutional layer 2. And the dots means the non-zero parameters, and the white part represents 0 parameters. So as you can see, after the pruning or sparsifications, the non-zero parameters and kind of spread out without any pattern. So from hardware execution perspective, and either we must still load the entire array to the memory and then for the execution, or if we apply any compression techniques, and we need pay the compression, the encoding and decoding cost. And that's why it doesn't result in much speed up in hardware execution. So at that time, we proposed the concept of the structured sparsity. Essentially, what we try to do is, if we define a structured group and try to have all the parameters within those groups to be 0 or non-zero. For example, the right-hand bottom again shows another relatively comparable examples. In this matrices, we trying to remove the entire row or entire column of the parameters. So the compression becomes a lot easier because we only need to index the row and column numbers. Okay, so it's a very simple concept many years ago. I guess, and the key here is to define the groups. And particularly for the CNNs, and when we explore many years ago, what we find, in fact, the groups can be defined as channels, filters. It could be the shape. It could also be entire convolutional layers. Depends on user's definition. So, for example, the entire depth, it's coming from the ResNet design concept as well, right? So with the group definitions, we can apply the group lasso as the regularizer, like over here, and add it into the loss functions during the training process. Well, I didn't explain the result over there a lot, but essentially our methodologies kind of leads to the real execution speed up, although our sparsification rate in fact is not as effective as the traditional pre-art. Well, later on we start our exploration with the CNN, and later on so we find it's very easy to apply to the fully connect layer and also other structures like long short-term memory. In fact, recent years we also successfully apply that to the transformer. So basically, the DNN models can compatible with the structure pruning technologies and kind of having more compact model for execution. So beyond that, we also have been exploring what we can do. In fact, we took multiple paths. One of the paths is how to improve this in compression or pruning techniques. Traditionally, in compressed sensing, a lot of such mathematical methodologies or techniques that have been explored. For example, L2 or L1 or L2 loss has been used. What we find mathematically, L1 term is not differentiable, and therefore when we plug into the DNN trainings, it's not that easy. And for L2s, what we find is it's a scale variant, means when the weight parameter is larger, it's pruning harder. Well, it gets smaller. The effect of pruning gets smaller and smaller. And this is controversial to our understanding, because in general understanding is bigger weight parameters and have a bigger impact, and we tend to save it instead of remove it. So what we propose at the time is to apply Hauer square regularizer. It's essentially is the square of the L1 over L2 ratio, like what I showed over here, okay? And compared to L1 only or L2 only, it is differentiable. It's also scale invariant, so it can be easily applied to the loss functions and to in the training process. More than this, we actually can apply Hauer square regularizer to the L2 norm of the group, and this means it can be combined with the structure sparsity technology. So again, I usually do not talk about the result a lot, but the right-hand side shows the Pareto frontiers on the structure pruning of the ResNet models. And of course, for the right hand, that means better accuracy, and for the top, it means the better efficiency, and our methodologies that have to perform than the pre-art. Well, goes to even deeper architecture level, because previously what I talked is more like algorithms and mapping to the memory structures, and it's a very loose connections. And then later on, we go to the deeper level. For example, right now, a lot of DNN models and people use fixed position representation for its high efficiency and better memory utilization. And with the fixed precision, on the other hand, at algorithm levels, the multiple kind of a precision or reduced precisions can be used. This is also induced by the high redundancy of the DNN models. So previously we talking about remove unnecessary parameters, and reduced precision basically is a reduced precision of the weight parameters, and so the data representation reduces. Well, the model can be more compact. Well, again, based on the past experiences, and we find across a different layer, the effective information representation can be different, meaning the precision level, the optimal precision level across layers could be different. It could be like in layer 1s and 2 bits is efficient, while in layer 7s maybe we wanted 4 bits. But critical question here is how can we find the optimal precision levels across layers? So in the past, I think people try like a neural architecture search. The challenge of there is the precision representation is discrete. So how to find or how to search such a discrete space is challenging, and also the combination is large. In other words, the entire search space is pretty big. So what we trying to do actually combine the fixed point and representation and the multi-precisions, and what we thinking, hey, can we kind of extend it and present it by binary one and zeros, right? And then if the entire, for example, MSB are zeros, and then basically we can shorten the representation without any change. Well, if LSB is zeros, and then we can reduce the representation by multiply by 2, okay? So that's the basic concept of our methodology, and we call them bit-level sparsity.
Question?
Sure.
I know you're also working in sort of adversarial AI.
Right.
So when you do this reduction, does that make you more vulnerable to adversarial attacks?
Well, that's a good question. The simple answer is yes. So it's like when I'm talking about the flexibility and efficiency are always the trade-off for the hardware design, and the efficiency and the reliability or the robustness of the model are always the trade-off pairs in the AI designs. So, but we also have some work is talking about if we carefully design the quantization methodology, sometimes it can be more resilient to the adversary attacks. So the concept of that work is we don't have to follow exactly like a binary representation. If we shift a little bit, for example, if I use an R1 device as an example, its resistance level, if we do not like say have an evenly kind of distribution, but have a nonlinear distribution, and then for the attackers, usually shoot for the linear kind of a representation to create adversary samples. So once we change this, and then the model have a stronger representation and better resilience to the adversary attack. Thank you. Thanks for the question. Any other question? Okay, so here actually is the continue the bit-level sparsities, and here actually is the exactly execution flow. What we have and start with the original, for example, weight vectors or matrices. We took the largest absolute values and space and do the normalization. And then the following process and followed STE process, which has been used for the not sparsification, for the fixed points and quantization a lot. And then we basically followed exactly procedure, and over there, we start with the bit level group plus those, and then change overall training objectives, and together with the original training objective plus the bit representation over here. Okay, the right-hand side table shows the results. Essentially, what we compared with our methodology with the pre-art methodology, well, quick summary is we can have a better compression ratio compared to here. The higher the better, and the better accuracy. Okay. So again, this thing can be combined with the structure tunings, and so one of the reasons we apply this or explore this methodology was it can be combined with the processing in memory easily. Okay. Well, next topic I'd like to briefly introduce is the neural architecture search.
One question.
Yeah.
That lasso loss function, can you use gradient descent to solve it?
Right. That's actually is an invariance, and it's differentiable term, and so we can directly apply to the loss functions. So the drawback of this is after applying this in actual term, the convergence of the training becomes slower. So our observation is usually it's take about 20 to 50% of the more epochs to complete the training. Yeah, so that is the real cost. But since this is occurs in the training time, not in the execution time, so especially prior, other people think this is acceptable. So another example I like to give here is the neural architecture search. I guess, I had some conversation with my colleague, and my colleague, his background is physicist, and he asked his kids to learn Python. And then I told him, and this is very bad news, I say, hey, as a computer engineers, and we work very hard in trying to automate the coding. And of course, right now, ChatGPT already made it happen, but he was very shocked when I talked about this, okay? So the first example on the neural architecture search I give here is a SkillNet. So very brief introduction on the neural architecture search, okay? So previously when we design the DNNs, and usually we start with some fixed structures and then manually tune the depth, the width, or the kernel size. And so neural architecture search tends to automate the entire flow to find a good combination of the kernels, the depth, and the width, and so on, so forth. Okay, and of course, then the optimization process is very tedious and takes a huge computation cost simply because the search space is very, very large. Okay, well, people have been dedicating in this area. For example, Professor Diana Makulis from the UT Austin, she has been working on how to improve the neural architecture search efficiency according to the hardware designs. The example I'm giving here is for the high resolution visual recognition. So what happens in here is when you have some semantic segmentation and pose estimations, usually on the images, and there are multiple objectives and will be fine, right? And the resolution of the different objects and could be very, very different. So in order to accommodate such a situation, in the past, we have to kind of build very complicated backbone structures and like illustrate over here. And then during the executions, is need to go through all the connections. What we do is we tend to search the depth for each brand, and also we try to fusion the connections. Because the observation is even for the different resolution of the objectives, and they share a lot of common features. So if we are able to build a connection and make the fusion structure of these features, and then we are able to reduce the complexity of the network and also make the execution more efficient. So here actually is one of the tests, and we had a website. Different teams submit their results, and here is our results. I know it's very, very small, but basically what I wanted to show is our matrix value is much higher than the others, and we do not need an actual training data for this neural architecture search. And the right-hand side is more quantitative results, and for the post estimation and also semantic segmentations. So in both cases, we get better results. But the key concept here is very simple. How can we fuse the feature maps from different resolution images? This is another neural architecture search example, and this is particularly for the 3D point cloud. Okay, so when we build, yes.
Doing the feature maps from the different resolution images, one of the key issues in a lot of AI is explainability, and I just wonder, does that help you with
So
explainability?
that's actually a very good question too. when we really build that, and we just do that algorithm to search, and then once this comes about the results, and we do find, hey, a lot of things are explainable. So, for example, at early stage and 3-4 years ago when we started, the search structure at the time we focused on the structure, like a kernel, the size is 3x3 or 7x7 or 9x9, and there are connections. And one of the observation is that it's always coming with more like 3x3, and that's in consistence with the later on at the time, like the ResNet or the existing very efficient network design already. So it's kind of indicating some connections. So, and here, for example, this work, we do see the connections, and if you really look into this and say the features they mapped and corresponding to the data we are giving, we see the correlation over there. I guess the difficulty right now is to, how shall I say, so once we get result, we can say, hey, this is reasonable. But it's very hard and to extrapolate in some rules at the beginning and applies to the search. So this part is not well bridged back yet. Yes?
Sorry, a follow-up question on this.
Sure.
I would assume that the optimal structure for different applications, different data sets would be different. It seems that you're implying there is a more general solution that would fit all. I'm wondering, what?
Are you talking about MIT's work, or you're talking about this work?
This work.
This work. This work is different. This work and what we search is the connections across different fusion. The fusion connections. So the backbone is there. So we have a backbone. For example, we build in several stages, and the stages and like stage 2, they have 2 branches, and for example, 3 we have 3 branches. So the backbone is there. We basically, according to the applications, to find maybe in fact not connection, all the connections that are necessary, and we search on how many layers it requires for each stage, how wide it is and for each stage. But general structure is there, like it's growing more fatter and shorter. The general structure is there. Yeah. So it really depends. And again, early stage, and for example, one of our work is to search the networks for phones versus in like computers. So for phones, and you can clearly see that the search structure is a lot shorter but wider. Well, for the computers, it's longer but kind of linear. That's because of the computing and the memory resources are different. Yeah. So this is another example, and this example shoot for the 3D point cloud. I wouldn't jump into this too much. So the key concept over here is we have 2 like first order and second order search. So the observation was for the 3D point cloud, the interaction and the dimension, they are both important. So we decided to decouple these 2 parts and handle or deal with them separately. The first order here is generally kind of trying to find the geometrical informations. For example, this dots and meaning the points of the 3D point cloud. And then the first stage, and we're trying to build connections across a different point. And then second stage, and based on some global informations, we try to kind of optimize and recalibrate the strength across in these connections. So in this way, in this 2-step and calibrations, and it can get better results. Okay. We also can kind of applying the NAS for the recommender system. Eric mentioned this at the beginning. So for the recommender systems, and it's this is actually a student's work when he had internship at the Menta. Recommender systems is very important, and this is to the companies, and the system itself is very, very large. The network itself is very, very large. So the effort of this work is trying to find the dense connections and to identify the different types of the interactions, and also the size of the interactions. So the approach itself is go back to the traditional approach, but the difference of the approach, previous approach is that we separated the dense and the sparse operations into two pieces and try to optimize them for each branch. Okay, that's the difference in comparison to the previous advanced search. Yeah. Yes. Go ahead.
So, could there be more of a continuum than just dense and sparse? I mean, you go from most sparse to most dense. Why do you just break it into two? Why not 3 or 5 bins in terms of sparseness or density?
Oh, you mean the kind of a sparse or dense levels? Or, okay.
That's right.
So here we have a rough and kind of an classification or categories, but dense and usually indicating like we have a very dense, like fully utilized, and sparse is very low. So I guess the concept here is more like for the data sort of features and used more frequently, or it's only used for partial of the data processing, so not all the data processing. I do assume like there's a way, since you have a more graduated kind of sweep over here for sure. But you can also imagine it's pretty like a quantization. We can have 8 bits and then goes to 4 bits or 2 bits, or if I have an 8 bits and then 3 2 bits, something like this. And the second approaches from implementation or training wise, it's easier than like the kind of a continuous way. Yeah, so that's the reasons that we have this.
I also thought it might be bimodal, that the stuff is either quite dense or quite sparse, and it doesn't really help to have gradations between them.
Oh, I see. But see, the something in the middle can be represented by the multiple sparse. You see my point?
Yeah.
And then it's more like what is the combination over here and how many over there? Yeah. So I guess in other words, it's more like a definition. How do we want it to realize it? Yeah. Yes.
So your approach is you're looking at a modular design, like designing a cell and then repeat stacking it? Or?
So originally, like 3-4 years ago, we started with those kernel design and connections. Right now, it's more like in this, for example, this structure already been fixed. We have many of the structures, and not many. We have a number of not too many. And then basically we pull from this, like we pick from this pool instead of just generally any combination. The purpose of this is to reduce the search space. Otherwise, if there are too many options, and the search space is too huge.
Yeah, but this one is the end-to-end network, or this is just one block and you can make it more deeper by stacking it, or like usually in cell-based search they design a cell like ResNet block, and then they make ResNet 34, ResNet 50.
So this is more like a block level.
Block
it's a little bit, yeah, it's more like a block level.
Okay.
Yeah.
And it is also, you have seen it is transferable, like if you are going from a simple problem to a more complex problem, you can just add more blocks.
More, but that's
Yeah.
what I said, the depth and the
Okay,
width.
okay.
Like what is the parallelism, like
Yeah.
how many branches, and depth is and how many kind of a stack.
Okay.
Yeah.
So a more complex problem can have more complex.
Right. All right. So now let's go to the algorithm and the hardware co-design. Again, here I give a few examples, and one of the example here is for the GAN design, generative and adversarial network design. It's also started with a few years ago. Of course, and again, right now, ChatGPTs and they basically use GAN, they use in general adversarial networks and to create the information. I think years ago, when we start talking about the GAN, compared to the like CNNs or DNN at the times, and it has a generator and also a discriminator, the two structures. And of course, the entire training cost is very, very high. And the second challenge is for the hardware design is in addition to, for example, convolution structures, and it's also have a transpose and convolution structures and kind of expanding the structure bigger and bigger. So how do we handle that at a hardware design level? So we had two works and to address the two problems separately. Early stage, and we, I mentioned I've been working on RM-based and processing in memory. So we propose and pin structures into process and GAN, and particularly for the GANs, and we discussed the pipeline structures in order to reduce the parallels, the training process across different batch. And of course, and here we must consider the data dependency. That is our work in back to 2018. And then 2019, and essentially we particularly interested in the transpose and convolution executions. And so if you come over here, what we find if we just shoot down some small basis structures, and then we do not need to handle all this in actual zeros. And of course, and there's some detailed pin structure corresponding to support the lower part in order to enable the higher efficiency. Well, this is a relatively old work, and so and then another recent work we call the escalator. So previously I'm talking about the structure pruning, and of course in the matrix and diagrams I illustrate over here indicating we could made large matrices in a very, very small size. But one thing you may realize that when we do this in structure prunings, and the rows and columns are still kind of random. There's no way to say, okay, let's prune rows 1 to 16, but save in 17 to 32, right? That's kind of not what we can control. This is where is to be removed, and really depends on the algorithm execution. So later on, what we find is such kind of randomness and also cause an hardware overhead. So escalator designs, and we trying to get mechanisms to better match the non-zero elements. So in this work, and for the input feature map and kernels, and we basically decompose that to some intermediate feature map and the basises. So each basises and have a different utilization ratio. So this is again back to this dense versus sparse and concepts. And for the basises use a lot, and then hardware-wise, and we prioritize these components. And for the basis and use and kind of less frequently, and then we can put a little bit away, depends on availability of the computing and the storage resources. And therefore, overall, so we target to the better kind of efficiency. In fact, a similar concepts has been growth. And for example, we last years we have this cascading structure pruning. This is in target on the data flow. So again, without the control the data flows, and what we find is in data use, I wouldn't say random, but hard to predict. What's occurring is in some pieces and like part of the input feature map have been used and then put away for a long time because the corresponding weight parameters are not available, and then we need to bring this back. So essentially, the observation is just to handle this data shifting without any controls occurs a lot of the overhead. So in this work, and what we're trying to do is reduce the redundant input activation fetch. So how do we do this? And we tend to kind of regularize or sequential the processings and for the weights. And for example, during the trainings, we put dense weights towards to the right, and then have some light use on the left-hand side. So if you're looking at this in cascaded process, we start with the full array processing because the input feature map has a full rank. And then the input feature map and through this specification or other mechanism gets shorter and shorter. And then the matrix is also getting kind of structured smaller and smaller. And then we are actually the executions and kind of getting more focused and focused. The similar concept right now we're working, the similar concept can be used in for, how should I say, like training processes. And for example, we can start with the 2 bits representation, 4 bits representation, and then to the 16 bits representation. So the advantage of this is we can start, because especially processing in memories and with SRAM or RRAMs, and we can start with the lower bits or higher bits execution, and then goes to the next bits and next bits. So we actually can sequential this and process and make the utilization like in a structured way. And here is the kind of CSPs and results, and because the input data can be reused and crossed in this filter trunks, and we hardware-wise, and we tend to capture this and reuse and prepare that for the next round of operations. And in this ways, and if it's not used, and then we can say, hey, this part can be stopped early, and we throw that, and we never have to come back again. And in this ways, and the communication cost and also the storage cost can be reduced. Okay. Yeah.
So sometimes they also recompute the activations, right? So rather than storing them, that you can checkpoint the activations and then recompute it when they need it for backpropagation.
Right. So I think that's for kind of the training processes, right? And this is more for the perception processes. So this is more predictable. Training processes, I think yearly we still kind of keep a lot of the information.
Right.
For example, in this process and during the trainings and even this in quantization, we need to in like one of my slides that shows in the back propagation stage, and we need to convert back to the full precision level.
Okay.
Yeah.
I have a question.
Sure.
So in the previous slide, you showed that there were 2 bits, 4 bits, and 8 bits. You can go like that. So in your hardware, you would have a certain bit precision of max.
Right. That's our ongoing work, and so it's not part of this work. And so hardware-wise, and for example, if you're talking about the processing in memory, right? One example is SRAM. SRAM, in fact, is all kind of a binary structure. So if you go to 4 bits, you essentially use 4 SRAM memory for each the cells and for each data. So this is essentially saying, hey, I can start with the left-hand side of 1 bits for a weight, and then 2 bits for a weight, and then so on so forth. Yeah.
But I was wondering whether this can be applied during runtime. Let's say if I decided I have more time than I expected, then I can still go higher for the accuracy. Back all these proof layers.
We didn't try that, but I think for example, dynamic neural network, it could be a good idea. So one of our work is doing, we design quantize the network, and then depends on the hardware resources, we give a certified accuracy. So here's the network, and if you decide it goes to the 8 bits, and here's accuracy we guarantee. And if hardware is not sufficient, you decide go to 4 bits, here's accuracy we can guarantee. So in other words, when you're talking about this, that is another possibility. So during the executions, if we like to changing across different possibilities, and then we can adaptively select the precision level. But we can discuss more. So my last part actually is an AI on real world applications, and here mainly I give some examples on federated learning. So federated learning, the concept was proposed by Google, I guess, in a few years ago. What they do is, first of all, the assumption is people wanted to keep their own data and hesitate to submit their raw data to the cloud and for sharing. It might not be necessary at all. And the second, the edge device and has an redundant, abandoned like computing power. How can we utilize those computing powers for the training process? So at the time, Google proposed a federated learning structure. So for example, Google had the server, and the server distributed the initial models to the devices. And each devices, according to use their personal data to do the training, and then they submit the trained update network to the server, and the server will aggregate all these changes, update the model, and then redistribute back the model to the edge devices. That's the basic concept. So through the practice, and people actually get some update of this methodology. So one challenge what we find is in hardware-wise or system-wise, and such a structure face the limited computing power at edge, and also the limited communication, like network bandwidth as well. So it really depends on like how big your application, how large your model, and how frequently you need this retrain, right? In Google's original setup, like the typing apps, and there are so many phones, and they only take a small number compared to the overall, the pool of phones, right? But if you really wanted to use for some dedicating applications, and then we do face the challenge of the communication efficiency. Some other things is every devices and face in different environment, and therefore their data are not uniformly in the same distribution. So we see personalization under non-IADs, and so the device have a specific data distribution requirement. We actually had two works, and over here, the first one is called the lottery FL. In fact, what we do is, if you heard about the lottery pruning methodologies, lottery sparsity methodologies, and in fact, what we do is at edge devices, and we apply this lottery schemes and created a sub-network. So the sub-network, of course, is smaller than the original one. And then during the data communications, we only send the gradients and of this sub-network to the server. Therefore, first of all, at the local, the training cost reduced because your model reduced it. And at the communication path, and its cost is also smaller because only a subset of the gradient will be communicated. Okay, so this is one of the work. Another work we call the mask FL. So in this one, we created a binary mask during the training. Obviously, this is cut off the communication cost, right? So compared to the federal large free FL, the structures and local can maintain the full model. So the locals and computation and processing capability remains, but it's only a small number of the gradients will be shifted. So again, as you can see, this target different application. Yeah.
Sorry, I know we've interrupted you with a lot of questions, but could you finish up in the next 3 or 4 minutes?
Yeah, sure, yeah. So I talk about applying AI to the applications, and here is the application. The application is the EDA, design automation communities, and people, what we do is the routability software designs. And so the right-hand side and illustrated a different federal learning setup, particularly for commodity applications, and different companies wanted to maintain their data. They really hesitate to share the data. But what we do is, we have 2 baselines, and one is local average, meaning if each user only do training with their own data, how is the routability, and then train centrally on all the data, and that actually is the kind of the golden case, right? Lower and upper bound. We try different federal learning setups, and essentially what we find is FastPath and plus and light fine-tunings and can reach very similar results as the golden results. So indicating federal learning can be applied to such collaborations across in different companies. Use the overall data without cross sharing everything. Okay. So quickly summarize and talk. We made this, and basically bottom layer is the hardware implementation, top layer is the algorithm exploration and characterization. Within this and domains, and there are many things that we can do. Maybe there are even more than what I illustrate over here. Essentially, I feel this and co-design concepts and still, first of all, it's valid, it's going to grow. We need to apply hardware constraints to the algorithm exploration, and then the algorithm capabilities need to bring back to the hardware implementations, and so we can adjust the configurations of the hardware design. Okay. Here are the reference on this talk, and I guess that's all I have. So
very good.
Thank you.
So, thank you. So, given the time, I think we've asked a lot of questions, so maybe it would be best, unless there's some really pressing question, to thank you very much.
Sure. Thanks a lot, Larry.
Thank you.
Thanks for the opportunity. Yeah.
Thank you. Glad you were able to do this. There's that.
Oh, thank you.
Yeah,
Okay. Thanks, everyone.
So our next talk will be given by Kailash Gogineni. Sorry, I butchered your name there. He'll be talking about scalability bottlenecks in multi-agent reinforcement learning systems. I think these sort of systems are very important for simulations and all sorts of things. Getting them to be more scalable is an important area, and look forward to your talk and enjoyed your paper.